Hi, everyone. Hopefully you can hear me OK. If not, tell me. So my name is Alon, and I'll be talking to you about native speed on the web, JavaScript, and asm.js. So we're talking about the web. It's the biggest open standards-based platform that we have. So it's a great way to reach people. You just give them a URL, and they can just get to your site, get to your code. So it would be great if it were fast, too, because then, hey, we could just send people directly to our code in the simplest way possible. So how fast is the web right now? There are many complaints. There are many things that are not as fast as they could be, and often the complaints are very justified. But just to clarify, so speed is determined by many different separate things, the DOM, graphics, JavaScript. This talk is only about JavaScript. So this is just one aspect of speed. Obviously, it depends on other things. So how fast is JavaScript these days? So again, there are many different factors to consider, the JIT, garbage collector, et cetera. But one way I think that's interesting to measure is to take a large real-world application, a native app, basically, and see how that works. So the Epic Citadel demo, which launched about 6 months ago, is one way to see. So I'm actually running in a browser now. This is Firefox. And I'll just launch the demo. So as I said, this is Epic Citadel. It's the Unreal Engine 3 from Epic Games. It's basically about 1 million lines of C++ compiled here into JavaScript. And you can see it running in the browser. So this is not using any plugins, not using Flash. This is just JavaScript and WebGL. And if you go to full screen, you can pretty much forget that it's not just a native app. And of course, it's fully interactive. You can walk around, look around. There's even a benchmark mode where you can see it's about 58 to 60 frames per second. So it's running pretty well over here. OK, so as I said, it's a large real-world C++ code base compiled with Emscripten into JavaScript. And the output uses just standard web technologies, just JavaScript and WebGL, as I said. And I think this kind of shows that you can run native apps on the web. This is a native app. It normally runs natively, but you can run it on the web, too, without anything non-standard. So as I said, this demo launched about 6 months ago, and you might have seen it back then. So what I want to talk about is what changed since then. So the demo itself, of course, is the same as it always was, but browsers have gotten better. So back then, when it launched, the demo only ran in Firefox. Not because there was anything special about Firefox, but because, again, it just used standards-based things. But it's a very large, complex app, and it sort of stressed some issues that other browsers had a few small bugs in. But many of those bugs were fixed. For example, in Chrome, today the demo runs in both Firefox and Chrome very well. Back then, the demo took about 20 seconds to start up. So startup includes parsing the JavaScript, running it, optimizing it. It also actually runs the game engine. So it's actually loading all the data from the file system. It's sending stuff to the GPU. It's doing a lot of work. This takes several seconds in a native build. So at the time, I was actually pretty happy to get to 20 seconds on the web. But today, if you run it in Firefox, it takes about 10 seconds. So it's gotten a lot better. And back then, this ran at about 40 frames per second in Firefox. Today, it runs in 60 frames per second in both Firefox and Chrome, as I showed you in Firefox. But again, it runs in Chrome just as well, same frame rate. And this is actually an understatement, because browsers cap the frame rate at 60, because there's no point in rendering more than the user can see. It just wastes processing power. So they can actually do much better. So there have been big speed-ups in just 6 months. So we've seen you can run a native app. Why isn't everything on the web super fast? So JavaScript engines do not always run at their maximal speed. All modern browsers have very powerful, complex JS engines that can do amazing things, but the JavaScript language has some aspects which make it tricky to optimize. So this is what motivated the asm.js project, which is basically an easy-to-optimize subset of JavaScript. So here's a small sample. If you know JavaScript, this should be readable, even though it's probably not the style of code you'd write by hand. So basically, there's a sort of, can you see the cursor? I guess so. There's sort of a Fibonacci-like function over here in the sense that when you call it, it returns the sum of the last two elements in the series, so x minus 2 and x minus 1. But it's not quite the Fibonacci because for the first and second elements, if x is less than 2, it returns a value from the heap, which you can see over here is just a uint8 array that is a JavaScript typed array. So it's the Fibonacci sequence, but the initial values are user defined. So this is JavaScript, but the asm.js subset of JavaScript, which this is easier to optimize. So why? Three things I want to point out here. First of all, there's this heap thing, which, as I mentioned, sort of represents our data or the memory that we're going to use. So the heap variable cannot be changed or replaced. It's actually captured by the function fiblike as a closure. So it cannot change later. The JavaScript engine has a static guarantee that whenever it sees heap over here, it's the same heap. It doesn't need to check if it changed. So that's helpful. This or zero stuff you may have seen on the line over here might look a bit puzzling. You probably wouldn't write that. But it's helpful because the or operator in JavaScript is a 32-bit operation. So it coerces its inputs to 32 bits. Or of 0 does nothing. So or with 0 just ensures you have a 32-bit int. So whenever things could underflow, like when we do x minus 2, we add an or 0, and we have a guarantee, in fact, that in this function, all the integer math can be done as 32-bit. So again, the JavaScript engine has a much, much easier task here. And finally, we use typed arrays when we need data. So heap here is a typed array. So given the fact that we know heap will never change, and we know that heap is a typed array, when we read heap of x here, the JS engine can literally just emit a load from memory. So this is as efficient as it gets. And this is why things like the Epic Citadel demo can run at very close to native speed. So here's a set of other benchmarks of asm.js. I can zoom in a little if that's easier to read. So these are all written in C++ or C. They're compiled into JavaScript with Emscripten. So we can compare directly native and JavaScript on the same code, which is nice. And everything is normalized to native. So the numbers are how much time it ran, how many times slower than native. And you can see Firefox and Chrome. So lower numbers are better. And you can see that on many of these smaller benchmarks here, both Firefox and Chrome are somewhere between 1 to 2 times slower than native, which is quite good, I think. On these larger benchmarks, the picture is pretty much the same. So there's Box2D and Bullet, real-world physics engines used in actual games. Java N-body is a large amount of Java code compiled ahead of time into C and then compiled into JavaScript. There's a benchmark of the LLVM. Actually, this is a garbage collection benchmark, so it's actually benchmarking a garbage collector implemented in JavaScript. And zlib is a compression library. So again, you can see both Firefox and Chrome do quite well, about half the speed of native on most of these. So let's focus a little bit on the Box2D results. So as I mentioned, Box2D is a physics engine. If you've played Angry Birds, then you've played a game that uses Box2D. It's used in a lot of other things because it's open source and it's great. And so basically, the data here was collected by JGW. And he basically took all the ports of Box2D from the original C code to everything he could find, and he benchmarked it all. So again, lower numbers are better. 1 is the original C code. And you can see multiple things here. There's a Java version. There's a few JavaScript versions. There's ActionScript or Flash. And there are 2 versions of JavaScript. There's the Box2D Web one, which is an older port that basically uses normal style JavaScript. There are objects and properties, et cetera. And an asm.js port, which is just compiling the C code directly to asm.js. And I think what's interesting to see is that asm.js is faster than typical quote-unquote JavaScript on the 3 browsers where both versions were tested. So just looking at the colors, you can see in orange Firefox on Box2D Web. And here, much closer to native speed is asm.js on Firefox. On Chrome, again, there's a speed up going to asm.js on Chrome 27. On Chrome 30, it's actually much closer to native as well. And even on Internet Explorer 10, there's a speed up from asm.js. So this shouldn't be a surprising thing because, as I showed you, asm.js is very low-level, simple, and easy to optimize. So it doesn't use a lot of things like the garbage collector. It doesn't need picks. It doesn't need all these tricks that are sometimes hard to guarantee that they run always fast. Things like hidden classes are wonderful, but they're hard to predict. asm.js is easy to predict. So just running asm.js on any browser should give a speed up. But what's nice is that if you really optimize for it specifically, which basically means optimizing typed arrays very well, and a few other things, you can get to where Firefox and Chrome are, which is about the same speed as Java. So that's pretty close to native. OK, so a bit of background about asm.js. It began as a research project at Mozilla. Basically, the idea was, well, every compiler generates some pattern of JavaScript. So there's many, many compilers to JavaScript, CoffeeScript, Google Web Toolkit. They all have a certain style that they generate. There were two compilers in the industry, Emscripten and the Mandrill compiler, that compiled C++ to JavaScript. Mandrill actually does a lot more, but it also compiles C++ into JavaScript. And over time, they experimented with various subsets of JavaScript, that is, various styles of output. But eventually, they converged on what turns out to be a very natural way to implement C++ in JS. It's basically what I showed you earlier, typed arrays for data, or zero, et cetera, tricks to guarantee types. So this pattern sort of emerged naturally in the industry, became useful. And basically, we thought, well, why don't we set out to formally define this subset so we can optimize it even further, maybe find some bugs in it, et cetera. And that's basically all asm.js is, a formal way to specify this pattern that grew sort of naturally. OK, so I've been talking about mainly Firefox and Chrome and how we can run sort of at native speed on both of those. Some of you may complain that I've not been mentioning Safari and IE, and that's very valid. The whole point of the web is that anybody with any web browser can access content, and it should look reasonably similar. If there are huge differences in performance, then the web is losing. So let's talk a bit about those browsers. So about Safari, the first thing I want to say is that all browsers are working hard to optimize JavaScript, but they focus on different aspects at different times. So here are SunSpider numbers where lower is better, and Safari is in blue. You should be able to see that it's beating all the other browsers. So it's debatable if SunSpider is the best benchmark. I don't think it is, but it measures a few things of merit, like startup speed. And this has been very important to Apple, apparently, and they've optimized for it quite well, beating out everyone else. So how do they do on asm.js code? They're great on that, or are they great on everything else? They're close on some things, farther on others. So Safari is in light blue, and like before, lower numbers are better. The numbers for Firefox and Chrome are basically the same as before. You can see on primes, for example, and on copy and corrections, they're pretty close. But on several others, they're a bit farther. And in fact, it's possible to see what the issue is. So on memops, they're several times slower. Memops, literally all it does is just hammer at memory, just reads, 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 writes, writes, writes. It doesn't do many computations on, so it doesn't do actual math. It just reads and writes, basically. So they've just not optimized typed arrays to the extent that other browsers have. But it's not that hard to do, so hopefully that'll happen. And they're not standing still either. They're actually experimenting with using LLVM as a JIT, which is pretty exciting because no other JavaScript engine has ever tried this. And potentially, it could give them very large speedups. We'll just have to see how the project goes. A few words about Internet Explorer. So IE6 was not a great browser. IE7 and 8 got better, 9, 10. 11 actually looks promising. So it's in pre-release. I'm not going to show you numbers because it's not the final version. I don't think it's fair to measure. But it looks pretty good. I've seen it beat other browsers on a few things. It supports WebGL, which is huge. First of all, for the standards process that they're finally playing ball with the WebGL standard, which it was unclear whether they would. So that's great. But it's also great because WebGL was the reason for the invention of JavaScript typed arrays. They were basically a way to give binary data to JavaScript for purposes of graphics. And typed arrays turned out to be useful for other things like asm.js. So if they're optimizing WebGL, they're optimizing typed arrays, we should expect asm.js to be fast. And that's probably why, as I mentioned, I've seen them do very well on a few benchmarks. So that's pretty promising. Overall, the big picture, just to summarize so far, JavaScript can run at about half the speed of native code, pretty much today on Firefox and Chrome. hopefully soon on other browsers. But of course, half is just half. We want to get all the way down to native speed. So what I'd like to talk about now is what are the remaining issues. So what's holding us back from getting all the way to native? So there are three that I'll talk about here. First of which are 32-bit floating point numbers. So JavaScript numbers are doubles. Doubles are 64-bit. Doubles on many CPUs take more cycles to compute. They're larger, they're more precise. Not too surprising that they take more effort, although on modern CPUs, often the difference is not big. But they also require more memory bandwidth. If you're constantly loading and storing 64-bit values, you're just pushing around twice as much stuff, and cache issues can crop up. And some simple tests on Firefox, basically just replacing all the double math with float math, shows that this could be about a 10 to 20% speed difference. So on relevant code, obviously code that uses floating point heavily, we might be missing about 10 to 20% of the potential speed that we could be getting. So can we actually get that speed in some manner? The cool thing is that it's sometimes possible to do 32-bit math as a pure optimization. So without changing the language at all, just optimizing existing code, sometimes we can achieve this. This code is not the most clever thing. It just creates a float 32 array. And then we assign to each element the sum of the other two elements. So 0 is the sum of 1 and 2, et cetera. Turns out that these additions right here can be done as 32-bit. Now, the reason is pretty technical, but the overall idea is that we're reading 32-bit values, because we're reading a float 32 array. We're adding them. And then we're storing them in a 32-bit array, so we're sort of rounding them to 32 bits. So in broad terms, how floating point math works is that when you add numbers, you're adding in, quote, infinite precision, as if you had that, and then you round afterwards to the right number, so to 64-bit in JavaScript. So what happens here, sort of logically speaking, is you round to 64-bit because it's JavaScript, and then you round to 32-bit. Turns out in many cases, you can just do the one rounding to 32-bit, assuming you're just adding two numbers. I'll talk more about that later, so it's not always true. But in this case, it actually is. And for that reason, it's possible for JS engines to optimize this type of code right now. There's no reason this should not run in floats. And in fact, there's some code in Firefox to do it. But as I sort of hinted, this is a fragile optimization. Just changing that to add a +1 here means it can't be optimized. This really depends on how floats are defined. So double numbers have a certain number of bits in the exponent. And it turns out that by adding 3 numbers, you can generate a crazy number that if you round it to 64 bits and then to 32, it's not the same as if you just rounded it to 32. So that's not great. But ES6, which is the proposal for the next version of JavaScript, has something called math.fround, which basically, as the name implies, rounds to an f or a float. And if we add a call to math.fround here, basically we add 2 numbers, we do fround, then we add 1, and then we sort of implicitly fround because we're saving to a float 32 array. This becomes optimizable. So using this approach, we actually could get a lot of the speed up of 32-bit floats. Not all of it. This might not work for every type of code, but at least we should be able to get some of that 10 to 20% speed up that I mentioned. OK, the second of 3 things that JavaScript is missing right now for being fully native is SIMD. So SIMD is single in instruction, multiple data, things like SSC and Neon. Probably most everyone here knows about those. So basically, instead of just adding 4 numbers in parallel, for example, you just create these chunks of 4 values. And then in a single operation, you just add the chunks sort of element-wise. So large parts of modern CPUs are dedicated to SIMD because it can be very efficient in some cases to just add these things in parallel when that's the type of math that you're doing, which often you are in linear algebra, which is for rendering and graphics and physics engines and games in general. And it's also possible to use this from C++, Mono, Dart. A lot of languages and VMs give you the option to access SIMD because the benefits are nice. So can we do it in JavaScript? There's a proposal from John McCutcheon from Google, who basically wrote a spec for how we could add this to the JavaScript language. Here's a small sample from the spec. So basically, we have a float 32x4 type, proposal for a new type in the language. You give it 4 floats, and it gives you this object, which represents sort of 4 32-bit values. And then you have a SIMD object with things like simd.add and all the other natural operations like multiply, et cetera. And these are immutable 128-bit values, so simd.add gives you a new one back. And this is basically designed for what CPUs provide. In fact, it's based on John's work doing the same thing for the Dart VM. And it's pretty similar in other languages and VMs too, because this is really what CPUs give you. You can't really change these chunks of values. You want to just create them and then use them, which create other ones. So experience with doing this in the past basically led to a straightforward spec that makes a lot of sense. As I mentioned, there are potentially big speedups from this, maybe even 300% if you're replacing 4 sequential adds with a single operation. And collaboration is ongoing with Google, Mozilla, Intel, and TC39, the committee working on JavaScript. So it's been very fruitful, and I think this will really start to happen very soon. There's no reason not to. The benefits are clear. There's a spec. So this looks pretty good. Threads. So this is the third of the things that JavaScript is kind of missing to be native. So the web has web workers, which let you use multiple CPU cores. It's actually had them for a while. And you can even transfer typed arrays. So you can create data in one worker and just give it to the other worker, which avoids copying. So you lose it, but the other one gets all the data. So this is pretty efficient. But you can't read and write to the same data at the same time. So this is good and bad. It's good because it prevents data races, which is a whole set of bugs that JavaScript just doesn't even allow you to have, because all you can do is just pass messages, and each thread itself can't race with itself. But of course, this is bad for cases where you really do need multi-threaded code, like modern game engines. They really do need to be able to potentially cause data races, although they're careful to avoid them. But they need the ability to just read and write from the same data. So what could be done here? There are a few proposals and experiments with code. But I would say it's pretty early in this particular space. There's no clear direction for what the right thing to do is. It would obviously require all vendors, all browser vendors, to agree to standardize something new, maybe complex, depending on which proposal, makes sense. And really, the challenging thing is not to implement it. We could tomorrow just let people access a typed array from web workers, from multiple workers at the same time. That's easy. We could just do it. But there are questions about how that fits in with the JavaScript language and the rest of the web, because the web doesn't have data races now, as I mentioned. So this will require some careful thinking. And again, this one is, I'd say, in pretty early stages. The importance of it is understood, but there's still no clear direction for what to do. So, but with that said, there are those 3 things that are missing. But even with all those things that are not quite there yet, many apps run at native speed. So I showed you the Epic Citadel demo before. I wanted to show you the JavaScript mesh demo, but it requires a network connection, so I will just tell you very briefly about it. The mesh project is something that basically emulates old CPUs, old machines like Ataris and Commodores. And it's a pretty large C++ code base. It's actually pretty complex to simulate old machines. The JavaScript mesh project basically just ported that to JavaScript. And you can actually run all these machines in your browser, which is quite cool. So after the talk, when I get to Wi-Fi, I'm going to tweet out a link to these slides. So you can just follow the link and actually play these things in your browser. But I think it's really a nice case for something that's very cool to do. And you can't do it if your browser isn't fast enough. So fast JavaScript makes things like that possible. Something that I do have a local demo for is, for example, this bullet demo, which is simulating exactly 500 cubes, basically just dropping them on the floor. But you can see it's rendering at somewhere between 50 and 60 physics frames per second. So again, this is about half of native, so native could have done about twice as many, but even 500 is kind of nice, I think. And for my last demo, I'd like to show you something a little different. So this is sort of a demo about first-person shooter or FPS games. So this might look a little bit familiar to you. This is the Banana Bread project, which ports Sour Brat, and I'll tell you a bit more about that in a second. What you might notice is that there's, aside from this sort of game that I'm running in now, and it's a first-person shooter, I can fire, can change weapons, etc. I can even add a bot, which will likely start to kill me. But you can see, yeah, I can just go into safe mode, and then I can create multiple bots that'll just fight each other. So this is a full first-person shooter. But there's also this thing over here. So you might think, well, that's a nice movie playing over there. But actually, it's not. It's a fully playable first-person shooter as well. So you can actually, if you're tired from playing one first-person shooter, you can play another first-person shooter in the first-person shooter. So this is basically Doom, although it's using the Doom code, but not the Doom assets because they're not open source. But you can just, by using different keys, start playing. And if you've ever played Doom, then this style of gameplay looks kind of familiar. And there's switches, and basically the whole Doom gameplay is here. And basically, and again, if you're tired of that, you can just switch back to the other game and have fun, etc. OK, so what did I just show you? Sorry. So what did I just show you? The outer game, the first-person shooter that I was in, is the Banana Bread project, which is a port of Sour Brat, an open-source game engine, basically from C++ to JavaScript and WebGL, so much like Epic Citadel, but it's open source and kind of smaller. Inside it was another first-person shooter, Boon, which is just the Doom code, specifically the PR Boom project, which has been working on the code since id open sourced it, and the free Doom content, which is a set of open source content for Doom-style games. And I don't know why slides are skipping, but how does this actually work? So I was running two games at once. How did I do that? So Boon, the sort of older style Doom game, runs in a web worker. And all I do is I just proxy input events to it. So whenever I press keys that I know are for the inner game, I just send it a message. And it renders its frames, and it sends me a message back with those frames, which are just typed arrays with data. And then I just push those pixels to a WebGL texture. That's pretty much it. So what was cool about this is that it took less than 100 lines of code to integrate them. So there's actually a link to the code here. When you have the slides, you can just take a look. And this, I think, I mean, we're talking about native speed here, but aside from speed, there are other nice things about the web. So it was really easy to do this. Once both games were ported, just 100 lines of code to integrate them, just basically the natural proxying of events and getting back frames. So it was a pretty nice, fun project to do. And getting back to speed, I think it's cool that you can run both of these games at 60 frames per second on a pretty average laptop. So this is just a ThinkPad with an Intel GPU running Linux, not the state-of-the-art in gaming speed. But it still runs those without a sweat. And even when I created multiple bots shooting, you could see it was doing quite well. And it's also worth mentioning the Doom game is, so it's using a software renderer. And of course, the game is quite old at this point. But the renderer was actually optimized for x86. So I didn't spend any time to optimizing it for JavaScript. So it's actually rendering at a much slower path than it would be for native. But still, it's more than fast enough to run, even though we're running both of these games at the same time. And there's a lot of GPU traffic just sending frames constantly. Still, it runs quite well. OK, so that's basically what I have. Just to summarize, so JavaScript is close right now and getting even closer to native speed. We can run basically native apps in many browsers, hopefully soon all browsers. And even on the missing pieces like SIMD and Flow32, et cetera, there's a lot of progress. So we've seen big speed ups so far, and we're going to continue to see big speed ups moving forward. And that is it for me. Thanks for listening.